Slide.
Okay, perfect. Okay.
Okay, good.
So yeah, please, you can entertain us with the quantum field theory of quadratic gravity.
Entertain you, yes, indeed. Well, thanks to the organizers, and hello to all my friends and colleagues out there that we haven't had a chance to get together in person for a long time. So I am going to talk about work that I've done with Gabriel Menez, my collaborator, though this builds on work that many other people have done, including many of the people that are in this conference. The early pioneers go back to Kelly Stell and Lee and Wick. There's a lot of activity going on right now, and there's things that we can borrow from other folks. What I'm going to do is take a quick tour through what I think are the main features without too much detail, but to orient everybody, since a 30-minute talk, I don't have time to develop everything, then come back and talk about causality and unitarity, trying to answer some of the questions that were raised by Professor Tuft. The basis for quadratic gravity is this Lagrangian, where I will neglect the cosmological constant as usual, but the main thing is that there are curvature squared terms in there. And this opens up an unsettled arena to work in, because these higher order terms do give you fourth order derivatives, and these higher derivative theories have problems for sure. And it's not clear what those problems really are until you get into them and work with them. I'm going to argue that we have a unitary theory. It appears stable near Minkowski, but it does have causality violations or causality uncertainties. If that's acceptable to you, then we're happy. I want to linger a little bit on this slide here, just because I am taking a particular pathway to make this discussion. And it's not exactly how we always teach or discuss things. We often start with classical physics. We do Hamiltonian quantization of free fields. We turn on interactions. And only late in the game do we get to the Lagrangians and path integrals. But we don't do that for things like the electroweak theory. In the electroweak theory, the very first thing you do is you don't start with massless Yang-Mills classical solutions. You start by coupling the gauge bosons up to the Higgs, and that starting point is important because it gives you the right spectrum to start with. So interactions there were important to begin with. So here I'm also going to do the reverse pathway. I'm going to start with a Lorentzian Lagrangian path integral, and both those phrases seem to be important. The first thing I'll do is the interactions with matter, and you can also have interactions with the gravitons themselves. Then I'll find the spectrum and learn some things about that spectrum, and then limit down to low energy and presumably classical physics, but basically get the standard effective field theory at low energies. With normal theories, these are the same. They may not be the same here. It could be that Hamiltonian quantization and path integral quantization are different. I don't know. We're in uncharted territory because they're strange theories. But this path is important because very early in the game, you find out that the only stable state is the massless graviton. There is a ghost with a negative metric, but it's unstable. It will then not appear in your unitary sums, you don't need to do the canonical quantization for it. There are ways to do it, but we won't bother. And the low energy limit looks like a standard theory. It's also, I'm going to stay Lorentzian. The equivalence of Lorentzian theories and Euclidean theories is not itself sacred. It does follow from the analyticity that comes from causality. We're going to have some changes with causality. And so we're not going to, we may not have the same Euclidean realization. So let's get started. The spectrum, both of these terms give you quadratic terms in the action, in the propagators, quartic terms in the propagators. In the spin zero portion of the graviton propagator, there's a either a tachyon or a normal high mass resonance state, depending on the sign of F0 squared. So we will avoid tachyons and choose F0 to be the sign that's written there. The Weyl squared term gives you either tachyon or an unstable ghost state, depending on the sign of its coupling. So again, we'll choose the sign to avoid tachyons. But it's the spin 2 part that's the dangerous part here. That's the part that we need to work on a little bit. So if you go and look at it in more detail, now here I'm going to include interactions with matter fields. And I have simplified this a little bit because this is certainly the right thing for matter fields. If I discuss the interactions of gravitons with themselves, I have to be a little bit fancier, but this has the essential physics. If you do the interactions of matter fields, you renormalize the coupling constant, and you also induce a logarithmic self-energy that goes like the 4th power of the momentum. So that will vanish as you get down to low energy, so that it's not going to give the graviton mass or anything. But the more important thing for us is that it picks up an imaginary part, and that imaginary part has been shaped by the normal fields in the theory, the matter fields, the q squared and the I epsilon. And I have to point out that my metric is the mostly negative metric, so that time-like momentum means positive q squared. So you get the self-energy with a positive imaginary part. That positive imaginary part is forced on you by the unitarity of the light states, of the normal matter states. And so you get the usual graviton, and you get there is this high mass state that carries 2 minus sign differences. So as you get close to that pole, you factor out an overall factor. The m squareds and q squareds coming backwards here. I put it in the normal form. There's a minus sign in the numerator, and there's a change in sign of the denominator to this. So now this is a finite width, but instead of plus I epsilon, I have minus I gamma. So those 2 signs is important. So it's different from a normal resonance. A normal resonance would have plus I there. It basically takes the I epsilon, makes it I gamma. Here we have changed those things. The interpretation that we're going to head towards, which is going to come in the second the more detailed section, is that this is a time reverse version of a resonance propagator. It's time reversal is anti-unitary, where anti-unitary means you complex conjugate everything. And so complex conjugating the I in the numerator and the I in the denominator is the equivalent of time reversal. It does still correspond to a decaying particle, and we'll see that in various propagators. But the important point that's going to allow unitarity to work is that the two changes in the sign simultaneously make the imaginary parts the same as a normal resonance propagator. So whether Z is +1 or -1, you get the same imaginary parts, and unitarity will be sensitive to that fact. So it will actually have a unitary theory. What you should see when you look at these propagators, so here's the propagators done in time-ordered form. The forward propagator normally carries what we call positive energies, and backwards propagator is the negative energy modes. Here, the reversed, the flow is the negative, the positive energy flows backwards, the positive energy flows forwards. Both of these are decaying modes, and the poles have shifted where they are. Basically, this pole here is sort of shifted over this way, this pole over here is shifted over that way. So it's an unusual setting, but that's what it is. So the energy flow is what's going. We gave it the cute name of Merlin modes. Merlin is the wizard in the tales of King Arthur who ages backwards in time. And the difference here is that we normally have these nomenclature of ghosts for this. A ghost is anything which changes the sign of the numerator. That's what was referred to as negative metric. This also has a corresponding sign in the denominator in addition. So anyhow, so now here's unitarity. Oops, let me back up, sorry. Let's spend a little time here too also. And the question is, when we do unitarity, who counts in the unitarity relation? Veltman asked and answered this in 1963 with the answer that only stable particles count. Only ones that are in the asymptotic spectrum count, and you're not supposed to make any cuts on resonance states, on unstable particles. Now that makes sense from the picture of the S matrix with asymptotic states in and out being the stable states. It looks very funny from when we normally do free field quantization, because we normally start off doing the quantization of free fields. You turn on interactions, things decay, and all of a sudden, by that little step of turning on the interactions, particles have disappeared. They no longer count in this unitarity sum. And so that looks very funny. And it's also true that we routinely violate this principle. We know that some states are almost stable. We treat them as stable, and you can call it the narrow width approximation, that you can treat these states as stable if you're not interested in their decay. However, Veltman is correct, of course. You shouldn't count any unstable state, any unstable resonance in the spectrum. That gives us a good news for this heavy ghost states. They don't get counted in the unitarity sum, only the stable states that they decay to. And Gabriel and I went back through Veltman's work, and it's not something that I can present well here. It's a fussy and very interesting presentation of the cutting rules. But all we had to do to modify that was to do about this energy flow. The energy flow was different for the Merlin modes, the ghost states. It's important that development stayed totally in Minkowski space throughout, because that's what we want to do. And anyhow, we end up proving unitarity for this type of state that decays to normal states. I'm going to come back and try to motivate that later. Okay, I won't go through the proof, but I'll motivate it later. The other issue that we run into as you go through here is that this type of theory has been known since the 60s to lead to violation of causality on short scales, on scales of the inverse width of these particles. And this is going to be traced in what I say later to this backwards in time, the fact that it's a time reversed propagator. So we'll see that in more detail coming up also. So there will be this causality violation on short time scales. It's roughly the inverse Planck scale. There's a coupling constant, but nevertheless. There's some phenomenology of this, but I won't go through the phenomenology at all, because it's all Planck scale stuff. Stability, I don't have a whole lot to say. We have Ilya Shapiro and Alberto Salvio are more of an expert than I am on this. But what Gabriel and I have done is just noticed that if you try doing perturbation theory, where you put a small disturbance in, these disturbances are decay and don't grow. So there is funny propagation backwards in time. Here's the backwards in time piece. So this is retarded boundary conditions, which normally propagate just forward. The use of forward propagation is unchanged. The backward propagation has a decay, is non-zero, but there's no sign of instability from this point of view. All right, so that's the end of the initial overview. So we identified the spectrum and this factor of these two factors of I changing in the propagator are the important things. So let's do a little bit more detail now on the causality part. The causality is not really cause before effect, because in fact you do have this backwards in time propagation here. So sometimes the effect happens before the cause, if you want. But the backwards propagation is shielded by the uncertainty principle. Basically, you propagate backwards a small amount that's given by the uncertainty principle. And in fact, that negative energy states are important to give the usual field theory definition of causality, which is that operators commute from space-like separation. You need that part there in the propagator to accomplish this. Which is now the standard thing that one discusses when discussing causality in field theory. This, if the operators commute for space-like separation, it limits the interactions to your backwards light cone. And so things outside the light cone don't influence you. However, much less discussed is we actually have an arrow of causality in the theory. What is it that determines what's the future light cone and what's the backwards light cone, and why do particles share that? And this is from this I epsilon, that it gives you the fact that positive energy propagates forwards in time. Since all our states, when we scatter states, they're positive energy states, they move forward in time, is determined by that I epsilon. But then let's trace back where that comes from. What if we'd used, if I'm doing path integrals, e to the minus is instead of e to the plus is? Now, when you're doing path integrals, this is the only place that I enters the theory. The action itself is real. The fields can be chosen to be, I'm chosen them real here. So the I that enters here is the determinant of later factors of I. If I do this, I want to, if I'm staying Lorentzian, I'm going to add a term that, with a little epsilon to make this better defined. I solve it by completing the squares, and I get the propagators out with the i's tracking the overall sign here. So if I started with a plus sign, I get plus i's. If I started with a minus sign, I get minus signs. So that's, you can trace the I epsilon back to your starting factors of I. You can, if the one with the opposite sign in the numerator, I mean, in the action, is the reverse time propagator. It's basically positive energies and negative energy reverse. So this has the opposite arrow of causality. One, it would have a future light cone and a past light cone flipped. You can make, this makes a lot of sense because again, time reversal is anti-unitary. When I do time reversal in the whole path integral, I flip the positive is to minus is because it's anti-unitary, even if the Lagrangian is invariant. So time reversal flips the factors of I. You can find this in canonical quantization by changing the factors of I there also. It's a little more painful to trace that to the I epsilon. And this is the side comment, but this arrow of causality has implications for what the philosophic puzzle of the arrow of time. Plus, the quantum physics actually do have an arrow of causality, and it's buried in the factors of I from the quantization process. We can do that discussion if we want. But for us, the issue here is we've now got quartic propagators. Quartic propagators have dueling arrows of causality. The usual part, the massless part, has the usual one. The heavy mass state has the unusual one, has the time reversed one. So who wins? And it's the stable states that win. If everything carries the plus I epsilon except the heavy mass resonance, it loses out and doesn't contribute. So you then get into a mode where you do that phenomenology that was before, that I mentioned before, and find out that there is real causality violation. And more importantly is there's causality uncertainty, because if all the interactions share this violation, on a small time scale, then all the timing becomes uncertain. So in general, this is even not in this quadratic gravity, causal uncertainty is likely a property of quantum gravity, just because fluctuations in space-time will lead to uncertainties in causality. And we have a paper coming up on that, but in this case, it's a true violation. Okay, so now here's the issues on unitarity. So when we do the unitarity, when we do Kutkowski's rules, you obtain discontinuities by putting the intermediate states on shell, as Gerard described. And on the far side of the cut, you use the time reversed or complex conjugated propagators. you use so several of the textbooks, like Peskin and Schroeder and Matt Schwartz's new book, don't mention that aspect of unitarity, but it's true. On the far side, you use the time reversed cuts. If you just do this then for a diagram, so a simple diagram like that we have in this one, you can, after a certain amount of massaging, you can repackage it, and you find that the discontinuity self-energy is like the decay width of whatever this external particle is. So this is the two-body decay width of that external particle at the momentum q. I've skipped that, but that's pretty simple stuff. If you put this into a resonance, and so now we're building up to development. You put it in a resonance, you have to do the bubble sum of all these. It's a slight violation of perturbation theory because you're summing a set of diagrams. But as you sum these, there are some where you use the reverse propagators and some where you use the normal propagators. You bubble sum each side with complex conjugate propagators. On the far side, the discontinuity in a resonance sum is then the imaginary part of the propagator. So D star, and then the width. This, as I pointed out before, is the same whether it's a normal resonance or one of these Merlin modes. The imaginary parts are the same for these diagrams. This is even true if you're using this in a loop. So here's putting a resonance in a loop. You do the sum. It's a little bit more complicated, but you play the same sort of repackaging games. You get the expected unitarity relation that in this case, I have this resonance mode to a normal particle and decays that way. So this continuity is still coming from the cuts on the stable particles. And then at this stage, you can see how you can get back from having the cuts on the decay products to having the cuts on the resonance when the resonance becomes very narrow. And this is a derivation which I hadn't seen before, but it's also not that hard to do. Basically, if you look at the discontinuity on this resonance propagator, which I derived was that way before, and you plug it in, this is actually close to a representation of a delta function. And in the limit that the width becomes very small, this is very highly peaked right at the resonance. It looks like a delta function and limits to the usual cutting rule, the 2 pi on shell state. So you get back the usual cutting rules in the limit the width goes to 0, even though you have only cut on the normal particles, the decay particles. And that's basically what Veltman did. It shows that all the cuts on the resonances are actually cuts through the stable particles. Basically, the I epsilon, the I gamma, the width part overwhelms the I epsilon. Resonances don't go on shell, and so they never appear in the unitarity sum. Only the stable states live there. And this then is sort of the heuristic way to see that you can get the same result with one of these Merlin modes with the 2 minus sign mistakes changes. The cuts through the normal particles, through normal resonances and these Merlin resonances are the same. You could even put them both in the same propagator. The unitarity sum works by cutting through the decay products. There is a twist. There is if you go back and try to do the unitarity calculation from first principles, not by doing it by taking the cut through the resonance to the stable particles, you actually find that some of your proofs go wrong. I'm not going to go through this for time reasons. This can be solved, and you can do it using what's called the Lee-Wick contour, which goes back to the times of T.D. Lee and Giancarlo Wick, where you go around the poles in a particular way. It gives you the normal resonances, the normal results as the width goes to 0. So that's a technical point, which I'm not going to really go into much. That's my roughly 30-minute summary of this. Clearly, there's more needed. The thing I think is most obviously not addressed is the stability issue. Stability at higher curvatures, where you can maybe excite that high mass pole. If it's unstable there, is it benign? I mean, in some ways you can think of Starobinsky inflation as an exponential runaway, but it ends up at a low curvature situation. So it's a benign instability if it is. We don't really know how to do many detailed calculations, such as higher loops. Gabriel has one explicit one of the graviton self-energy done at next order. It's actually a very difficult calculation. It's not yet published, but it'll make it there eventually. Can we connect, since the claim is that unitarity works here, can we use unitarity techniques to do calculations? Can we convince ourselves by simulating this on a lattice, etc.? So here's my quick summary. I think I'm roughly on time. The quadratic gravity is this renormalizable field theory. It has many positive features. You get the massless graviton. The heavy resonance decays, doesn't appear in the asymptotic spectrum. It seems stable under perturbations. It's unitary. It's unusual feature. The thing you have to give up from our standard lore is this is exact causality. You get causality violation at the Planck scale. We can't claim that this is a perfect theory, but it appears as an option, a viable option for quantum gravity at this stage. So that's my quickie summary of this topic.
Okay, thank you very much, John. Okay, yeah. So I think we have 3-4 minutes. Yeah, let's say 3-4 minutes for questions. So let's see first. Yeah, so there is Richard. Please, Richard, you can unmute yourself. Richard Woodard.
Okay, thanks for this summary of your work, John. I have just one question. What's the classical limit of your theory? And I want to know what the dynamical variables are and what the Lagrangian is.
Yeah, so I mean, this seems to limit very nicely to the effective field theory description, where your only low energy degrees of freedom are the graviton and the matter fields. The only unusual feature of that is there is a sign of the higher order terms in the effective Lagrangian that's different from what many people would expect. That's tied by the fact that we get the spin 2 is not a ghost, is not a tachyon, but
so is it a metric theory? I'm confused.
Yeah, it's a metric theory that's
what's the Lagrangian?
The Lagrangian at low energies is the Einstein action.
No, you're purporting to give me an exact theory. I want to know the exact Lagrangian.
Well, the low energy theory is the heavy modes decouple. And so my low energy theory, if you want to know what the degrees of freedom are, you just
How can I
look at
know
the
that
low energy.
unless I actually have the classical limit of the theory to look at?
Yeah, but this is how, I mean, effective field theories work. Is as you go to low energy, the high energy degrees of freedom decouple, and you have an effective low energy Lagrangian. And the effective low energy Lagrangian here is Einstein.
But again, this is not an effective field theory. You're purporting to give me an exact theory. I want to know what the exact classical theory is.
Right, but
If you
that's what
don't-
I'm saying. Is
If you don't have the answer, that's okay.
Yeah, so
I won't
don't
keep
know
pressing.
the answer at high curvatures. So I know the answer in the limit of low curvatures. And the answer in low curvatures, low energy, is it's the Einstein action. The classical theory at high curvatures.
But then how is
such
that
a thing is
different from
defined?
effective field theory that you have been the principal exponent of, just using the Einstein theory as effective theory?
Right. Yes, and so it limits to that theory, and then from that becomes the classical theory. And so at low energies, low curvatures, I think the answer is just it's Einstein. If one were to try to define a theory at high curvatures, that I'd have to. I'm not even sure the classical phrasing makes sense there. That's the important point.
Okay, maybe we can also keep discussing about this point in the discussion session because it's very interesting also about the correspondence principle. Maybe we can just have one more question. Alessia, very quickly.
Yes. So hi, John. Thanks for thanks for the nice talk. So I have just a quick question. So you mentioned at the beginning of your talk that eventually your approach can match the results of the approach of Anselmi, but I really don't see any straightforward connection between the two approaches, since what you are doing is just to include one loop corrections, and this makes the ghost of stellar gravity unstable, while in Anselmi's approach, the idea is to change the Feynman prescription such that the ghost, so the fermion, contributes with the zero residue to the propagator. So can you clarify maybe the connection?
So I had the comment that I hope we can meet up with Anselmi at some stage. In other words, I think at the present time, I'd have to say we're having distinct starting points, because he very clearly wants to start in Euclidean space, and then by working at it carefully, to decouple some of these states as he goes to Lorentzian space. And that's not a guarantee that that's the same thing that I would be doing starting in Lorentzian. So I don't know if we're equivalent at this stage or not. I'd say that's in the more work to be done section.
Okay. Thanks.
Okay, nice. I mean, I think we will have many more questions in the discussion. So we can just move to our third speaker. Let's thank John again. So yeah, hi Roberto.
Hello.
Hello. Please, you can share your screen.
Yeah, let me start.